Then let's start today's. So, good evening, everyone, and welcome to the second live session for the course Basic Real Analysis. So, today, uh, we'll start with the sequences. So, I'll do a few problems on sequences of real number related to its convergence and some of the conceptual question. Okay, and then we'll move to topological things mainly based on closed set. Okay, because it has that's what has been introduced in this week. Okay, so for this week 2. So to begin with, let's start with this some computational problems. Okay, so no, let's start with this problem first. So question is that suppose xn is a sequence given to xn is a given sequence of real number such that xn converges to x, okay, for some x belonging to real number. Okay, now the question is, so the first question is that xn raised to the power n converges to xn. Is this true? The second question is uh, that okay, fine, this is the only problem. Okay, so yeah, so what do you feel?
So it should be true, sir.
Okay, no, but it's not true. Okay, so I understood why you said, that's why I wrote question in this fashion. So basically, see, it's true.
If sequence xn converges to x, then by algebra, sir.
No. See, this is the problem. I mean, the problem says that xn raised to the power n.
Or is
Suppose,
n tends to infinity? Yes, sir. Yes, sir.
so if there was alpha, then you could have said,
Yes, sir. Yes,
okay,
I understood, sir.
yeah. So for any alpha, maybe like it could be any uh, a real number. Okay, but the problem come. So this is a is true. Okay, so this is true. So I am not going to
Sir,
prove it, but it's
sir, I
obvious.
have the counter, sir.
Okay, you have counted, just a second. So xn raised to the power n converges to x raised to the power n. Okay, yeah. So tell me the counter example that you have.
Sir, for B, sir.
Yeah,
Sir, A is true, sir.
a is true. I am not proving it because it's very
Yes,
easy, one can do it
yes.
very easily. So let's talk about the
Sir,
b part.
yes, sir. Sequence xn is equal to n to the power 1 by n.
Xn 1 by n to the, sorry, what did you say?
No, sir.
N.
N to the power 1 by n.
Correct. So what is the
Yes,
limit
sir.
of xn?
Sir, 1.
Okay, so okay, again I am not proving this, but one can show that limit of xn is going to be 1, right? Now what about xn raised to the power n? This is going to be n, and we know that xn, so yn given by xn raised to the power n diverges to infinity.
Yes.
Okay, okay, now can you tell me how to prove this limit of xn is 1?
Sir, by Cauchy's second theorem, sir.
Okay, what's that?
Sir, if sir limit of an plus 1 by an exists, then it will be equal to limit of an to the power 1 by n.
Correct, that's true.
Yes.
Okay, so you can use that.
Sir, by sir sandwich theorem also it can be proved.
Yeah, correct.
Can be proven, sir. Yes, sir, it
So
can
for
be
that you
proven,
will
sir.
have to probably use this logarithmic thing, and then you can probably work with that, right?
Mm.
I mean, or otherwise, like sandwich, how do you use? You cannot use directly here, right? So what I'm saying is, okay, so let me say this first. So I'm saying you better define yn to be kind of log of xn. Okay, so this will be turn out to be n upon log of n. Okay, and then now you can use this sandwich theorem to show that this goes to 0. okay, and then you can show that xn, which will be exponential of yn, this will go to 1. Okay, so you better try to show this, but how this happens. So here you can use probably uh, this sandwich theorem, but you cannot apply it directly, because whatever bound you get, n is not bounded above, right? So you cannot get any constant, right? So if you would have gotten some constant over here, then you can do in this way.
Yes, sir, greater than 1, sir.
Yeah, but the point is you can't get this upper bound. That's not
Yes,
possible.
sir, yes.
Okay, so that's one of the issue. And okay, and what you suggested is much better. So for that you can use this theorem. So this is first method. Maybe the second method could be that limit of an 1 by n equals limit of an plus 1 upon n if both exist, right? Okay, I'll write the general theorem as well. Okay, I'll write the general theorem afterwards. So this is going to be equal to this if both limit exist. Exists, and we know that this is, one can easily show that this is nothing but limit n plus 1 upon n, which is equal to 1. Okay, so that's an easy problem to do. Okay, so here we found an example where xn is converging to 1, but the nth power is not converging, it's diverging to infinity. Okay,
Sir, we can also take a simple example, constant sequence, sir.
Correct, that would be the most simplest thing to do, right? But it depends, like the constant. Okay, that's also one
greater than 1, sir, greater than 1.
Yeah, but still, if it's, I mean, if it's less than 1 also, then also it will work, because okay, so let
yes,
me
sir,
write
then
it.
that limit will converge to 0, sir.
Exactly, but the constant is going to c, I mean, it's not
Yes,
0.
yes.
Okay, so maybe this is the first example. The second example could be, as you suggested, that xn is just constant sequence, and suppose c is non-zero. Okay, so and then when you define this xn raised to the power n, this is c raised to the power n. Okay, and there are two cases. So limit of xn raised to the power n will be infinity if mod c is greater than 1. Actually there will be three cases. Okay, and limit xn n will be equal to 0 if mod c is less than 1. This will be limit of xn raised to power n would be 1 if c is equal to 1. And the fourth case would be that limit xn raised to power does not exist exists if c is equal to -1. Okay, so this is the only case where the statement is true, right? Because the c is also 1 and xn raised to power n also converges to 1. So in this case it's true, but in the other cases you can clearly see that the statement is not true. Okay, so that's why overall this statement is false. Okay, this second statement. Okay, so now let me write the theorem. Okay, the most general theorem. So this is the result. The result says that suppose you have been given a sequence, so let xn be any sequence of real number. Okay, then you have following identity. So that is lim inf. Okay, so this, like, I'm talking about this theorem. Okay, so here xn plus 1 upon xn and xn raised to the power 1 by n, what is the relation? Okay, So the general relation is like this: xn plus 1 upon xn. This would be less than equal to lim inf of xn raised to the power 1 by n. Okay, and again this is let me cut and write it here. Okay, and now you obviously know that lim inf is always less than equal to lim sup of xn raised to the power 1 by n, and this is less than equal to lim sup of xn plus 1 upon xn. Okay, so these are the main thing. So this is an obvious statement, this one. The main thing is that this is true, the first inequality and the third inequality. Okay, so here also I should write one thing. So be sequence of positive real number. Okay, because otherwise this xn raised to power 1 by n might not make sense. Okay, so a sequence of positive real number. Okay, so this is the result. Now, as he pointed out, that if both the limit exists, then that has to be equal, and this is just from here, because once you know that this limit exists, means that lim sup will be equal to lim inf. Now once this the first term is equal to the last term, then obviously the middle terms are also equal to that, right? So that's why when the limit exists, it has to be equal, like all the limit has to be equal, both the limits. Okay, okay, so this is the general statement. Now based on this, let us see few problems. Okay, so this is the second problem. Okay, so find the limit for the following sequences. Okay, first let me see. So it is
Sir,
n factor.
sir, can you show these inequalities, sir?
If you want the proof, maybe I can give it in the next class, because I
Yes,
don't
sir.
remember exactly how to prove it. But if you want, I
Yes.
can surely give it.
Okay.
Okay. So based on this, we have this following problem. So let's say n factorial upon n raised to power n e minus n 1 by n. Okay. And then the second one is n factorial square upon n raised to the power 2n whole raised to the power 1 by n. Okay, so these are just direct application of this thing. Okay, so what we need to do is, in this problem, so here in the first case, let me divide in two parts. Okay, so the first case, you know what xn is, you just have to find limit for. So here xn is given by n factorial upon n raised to the power n. So can you calculate it and let me know what is the answer? You do it by yourself.
Yes, sir.
Okay, yeah, parallelly if you do, it would be better.
Sir, E.
You are getting E?
Yes, sir.
Okay, just a second. Okay, so this will be E, and this is 1 upon. Aren't you getting E? How are you getting E? So this I can write it as, it should be 1, no? Yeah, can you check?
Yes sir, yes sir.
Yeah, so the limit, if you take xn plus 1 upon xn,
1 plus 1 by n to the power n is going to e.
exactly. So this is e times 1 by e, which is equal to 1. Okay.
Sir,
So
I take this limit as 1 sir. That's
no, no,
why
no,
I
no, no,
got
no. Okay, okay. So let me write it here. That limit 1 plus 1 by n raised to the power n goes to e, or is equal to e. Okay. Okay, so what we got over here is this limit is going to 1, and hence now using this result I can say that limit exists means this lim sup and lim inf are equal. This would force that limit xn raised to the power 1 by n exists, and limit xn raised to the power 1 by n will be equal to 1. Okay. So this is how, whenever you see a problem which is of this kind, like 1 by n something is there, then you have to deal in this way. Okay, otherwise you use logarithmic thing, as I pointed out over here. Otherwise you use log, and then you try to deal with the deduced sequence, which is after taking log what you get, and then you can conclude about the xn original sequence xn once you get information about log of xn. Okay, so this is another way, but this is much more simpler. Like you just use this, evaluate this xn plus 1 upon xn, you'll get a simpler form. Just try to study the limit of this thing. Okay, similarly you can do for the second one. Okay, so I am leaving it because I don't want to go in this calculation, but one can easily do in a similar way for the second one. Okay, do you have something to say? Okay.
No sir.
Okay, so I'm leaving it to you. If you want, I can give you some time. If you want, you can try it right now as well. What do you want? Should I proceed, or do you want to try?
Power minus 2 sir.
Hmm?
I think e to the power minus 2.
This one?
Yes sir.
Okay, then I'll have to, if you want to verify, let me just.
No sir, just wait. Yes sir.
Yeah, so this would be n plus 1 square, and then n plus 1, 2n plus 2, 2n. Yeah, so this is, again what you get is 1 upon 1 plus 1 by n raised to the power 2n, right? And this is going to 1 by e raised to the power 2. This is what you get, e minus 2, right?
Yes sir.
Yeah, okay. Okay, so this was about this result. Okay, now let's go to some other problem. So again, like I'm writing the sequence, you have to tell what will be the limit, or whether it converges or not. If it converges, what will be the limit of that sequence? Okay, so xn, let's take this one. Okay, so okay, fine, xn plus n sine square, and then you have n plus cos n. Okay, first tell me, like, what do you think? Looking at this sequence, what do you feel? At least you should have some intuition, like whether it will converge. If it converges, what should be the limit? Do you have any guesses?
Sine square.
Sine n square upon cos n. I mean, these are sine of n square, so this is not sine square. Okay, I think I missed it, sorry. Sine n square. Okay, so what do you think? Vaguely, can you say something? Okay, so see, like what do you see in numerator? It's n plus something, but this is a bounded quantity, right? The sine square n square can take at most value 1.
It should go to 1, sir.
It should go to 1, right? Because this is n upon n kind of thing. This is bounded thing, so you can better ignore this, right? So you are getting n plus something upon n plus something, which has a bound. So that the limit should be 1, right? So my claim would be that limit of xn is equal to 1. Okay, so now let us try to prove it. Okay, so now we'll try to do it just using the definition, okay, what we have in our mind. So first, what should we do? We should choose some epsilon be any real number. Okay, now we need to evaluate this difference. So mod of xn minus 1, this is nothing but n plus sine of n square upon n plus cos of n minus 1. Now just do the usual computation, or let me write here itself. So this is n plus cos of n, and in numerator you see n and get cancelled, so what you are left out with is sine n square minus cos of n, right? This is what you get. Now what you can do is now you can use this thing, that this sine n square and cos n, what do you know? They are bounded. So I'll bound it by 2. So I'm using triangle inequality a plus b is then equal to mod a plus mod b in numerator, and in denominator what I'll use is a plus b is less than equal to mod a minus mod b whole modulus, right? This is what I proved in the at least the second one I mentioned in the last tutorial, right? So I'll use that because I need a lower upper bound for this quantity. Okay, so that's why what I get is sine n square plus cos of n upon this is n minus mod of cos n and whole mod. Okay, but we know like cos n is going to be at most 1. Okay, so there is no meaning of this modulus because this is always going to be positive because n is greater than and equal to 1. Okay, okay, but one thing here, is there any possibility that this will become 0? That is, otherwise we cannot write, correct? Or I should have asked this in the beginning. Okay, so when I am writing this itself, what about this thing? Like, what if it becomes 0?
Sir, it will become a 0 at irrational number.
Why?
At pi by 2.
Cos of 0 is 1, right? Cos
yes,
of
sir.
okay, I mean, okay, if we are talking about this one, then for this to be 0, this would imply that cos of n equals minus n. Okay, so in this case it's, so we know that cos of n could be at most 1. So only possibilities, so and we know this is positive, right? So n, I can say this belong to minus 1 minus 2 dot dot dot, and cos n can at most achieve minus 1. That is the only possibilities. So cos n will be minus 1 if and only if n is equal to pi, okay, which is not true. Okay, this does not belong to the set of natural. So what you were saying for this one, it's true, but over here that logic will not work, but you can similarly argue.
Sir, 0 at 0, sir.
Yeah, so at 0 there could be a possibility.
But n cannot be 0, sir.
Exactly, that's the thing. Okay, okay, so now, so that's all. So we can write this as 2 upon, now you see cos n is always modulus cos n is less than equal to 1, so minus
but there is a modulus of cos n, sir.
But still the same logic would work, right?
Yes, sir.
So anyway this is not going to be 0, that's what I mean. So maybe I should just point it out here that this quantity is non-zero. Okay, now over here I know that mod of cos n is less than equal to 1, so n minus mod of cos n will be less than equal to, sorry, greater than equal to n minus 1, so 1 upon this would be less than n minus 1. Okay, and now you know this, you can make it less than epsilon for n greater than equal to n naught. Okay, n naught that you can write in terms of epsilon. Okay, so maybe n naught depending on epsilon. Okay, so this proves that limit of xn is equal to 1. Okay. Okay. Oh, sorry. Okay, so now let's go to the next problem. This one is quite interesting. So maybe you can write this cos of n would be cos of n factorial a upon a times pi, where a is some rational number. Okay. Now, what about the convergence of this sequence xn? Okay, so I'll give you some time. You better think on this. Did you see any property, like any special feature about this sequence?
सर ये प्रॉब्लम सर रूडिन की बुक में है शायद सर.
That doesn't matter. Okay, so let's start to deal with this. So see, what is the advantage of q, rational number, that you can write in terms of p by q form, right? That is the definition of rational. So suppose that let a equals p by q, okay, where p belongs to z and q belongs to natural number. Okay, now, okay, tell me one thing, that suppose a is not there. Okay, suppose I am just talking about n factorial pi, or just n factorial. What do you know? That n factorial is always going to be even, right?
Except 1.
Except 1. So anyway, when we are dealing with sequences, we are looking for larger value of n. So this is for n greater than 2. Okay. Now the point is, when you, so okay, why I am saying this? Because what I know is cos of some even multiple, or 2k pi, is equal to 1, right? That's all we know about cos. That's why I'm stressing about this n factorial. Okay, so if I forget about a, I know that this is going to be even number. Okay, so n factorial of pi would be just 1. This sequence will be 1 if a is equal to 1. Now, when a is of the form p by q, okay, that, so if my n, suppose n is greater than equal to q, okay, and q suppose is, okay, so there will be two cases when q is greater than equal to 2 or q is less than 2. Okay, so what I mean to say, roughly, let me first explain, then I'll go to the formal writing. So roughly what I want to say is that n factorial, I'll write it as n minus 1, n minus 2, dot dot dot. So q will be there, q minus 1 will be there, and ultimately I need 2 also. Okay, and then p by q. So this q will get cancelled with q. Suppose I am taking n to be very large, okay, for now. Okay, so if I am taking n to be greater than equal to q, I have this kind of information, or even much larger you can take. So suppose q is 1, then in that case this will fail. So I am saying just suppose q is also large, then in that case you can clearly see that this is going to be even number because of 2. Okay, now the only case is where it will fail is when q is equal to 1 and suppose q is also equal to 2, then in that case this q will cancel 2. Okay, so that's a problem. Fine. So what you do is, So here you assume that q is strictly greater than 2. Then this argument works. Now in this case, when q is 1, what you can say, n factorial p is going to be even. There is no issue. Even for n greater than 1. Right? Now when q is 2, okay, so let me write here even for n greater than 1. In this case, n factorial p by q would be what will be the expansion? So the 2 will get cancelled by q. So what you have is n minus 1 dot 2 times p, 3. Right? This would be the expression of n factorial times p by q. Correct? So here just write 2. Now for this, okay, anyway I am working with n greater than 2. Right? But here if I take, so this is only possible for n greater than 2. If n is equal to 2, right? So if n is equal to 2, then obviously this will cancel out. So there will be no term like this. So in that case, our argument will fail. Like no one guarantees that this will be even if n is equal to 2, first, let's say. If n is equal to 2, this expansion does not make sense, right? Because you will, so let me write properly, or let me write just as a case. Okay, so if n is equal to 2, what you have is n factorial p by q would be just p. Okay, so what you need to do, even if you take n equal to 3, n factorial p by q would be 3 times p. Again, there is no guarantee. So if you take n equal to 4, then n factorial p by q would actually include 4 times 3 at least. I mean, there could be other number. So in this case, you will have n minus 1, at least 4 you will get, and then 3, and then 2 will cancel, you will have p here. So in this case, see, because of 4, you can say that this is going to be an even number. Okay, so what I mean to say, so I hope this is clear to everyone, what I just said.
Yes, sir.
Okay, so this is the main thing what you need to focus. So over here, what I'll just write is, so how should I write? I can make it smaller probably. So what I can say is, so let's first write this, what is n factorial p by q. Okay, so I'm assuming for n greater than equal to q, okay, I can write this n factorial p by q as n minus 1 dot q plus 1, and then q will be lost, q minus 1 dot 2 times p. Okay, so here I am assuming n is greater than equal to 2 as well. So n strictly greater than 2. Okay, then I can write this expansion at least. But what if q is equal to 2? No, I cannot write. So let's break into two cases. Okay. Okay, so let me write for q equals 1. Okay, in this case, n factorial p by q is equal to n factorial p, which is even for n greater than equal to 2. For q equals 2, what I can write is n factorial p by q will be equal to, so n times n minus 1 dot 3 p, okay, for n greater than equal to 2, or should I write 3 probably? So let's write it 3. Okay, we have this formulation. Now this is not even, so I'll have to take, so n factorial p by q is even if n is greater than equal to 4, because then 4 will be there. Okay, okay, so this is what I get. Now for general q, for q belonging to q minus 1 comma 2, okay, in this case what you have is for n greater than equal to, so that means q belong to q and q is, okay, sorry, I should not write this because q is in natural number, right? So q belongs to n such that q is greater than equal to 3. Now in this case it's much more simpler. So you take for n any greater than equal to q, then in that case you have this representation. Okay, so now in this case you know that this is even for n greater than equal to 2, right? So this is fine. Okay, because n I'm choosing greater than equal to q and n greater than equal to 2. So if I combine all these cases, what I need to make sure, so combining all cases, what I can write is combining all the possibilities for n greater than equal to, let's say, q comma 4. Okay, maximum of this 4 comma q, we have n factorial times p by q is even. Hence xn is equal to 1 for n greater than equal to n naught. So let me write this as n naught. Okay, for n greater than equal to,
Sir,
yeah,
sir, when you are writing sir p by q, then you are assuming that GCD of PQ is 1.
yeah, okay, so that is I am assuming it. Okay, so because I
Sir,
mean,
when you have written q is equal to 2,
that could happen, right? What if p is 3?
sir, no, when q is equal to 2, sir, what you have written is factorial n into p by q is equal to that thing and is odd. You should have written
Where
q is equal to 2, sir.
if q is equal to 2, then I'm writing this representation is fine. I mean I can write this formulation. Now what you are saying, this is going to be odd?
No, sir.
What's your question?
Or n greater than or equal to 3, sir, you have written, sir. And then you are writing n greater than or equal to 4.
Correct, huh?
So this is not clear. Why?
No, okay, let me repeat what I wanted to say. I'm saying that if I take q to be 2, then n factorial p by q can be written in this form. I mean this is equal to this. And why I choose n to be greater than equal to 3? Because I want to make sure that 3 is at least here, so that 2 get
Okay,
cancelled.
sir, it's clear, sir.
Okay. Okay. Okay, so then you can see that xn is going to be 1 for all n greater than equal to n naught, and this will prove that limit of xn is equal to 1. Okay, so now let's move to some other problems. So is this fine to everyone?
Yes, sir.
Okay, so now let's proceed further. Let me see.
Sir, here, sir, p by q is not fixed, na, sir?
P by q is fixed, right? So I'm saying this a is given to you. A is not varying on n. So initially
Okay,
you
sir.
have a. Okay.
Yes, sir. Then we are calculating all these things.
Exactly. So a can have different possibilities. You don't know what rational number is someone is choosing. So depending on rational number, my choice of n will depend. That's why
Yes,
what
sir.
comes at the end. At n has to be at least greater than or equal to this 4 in maximum of these two, 4 and q.
Yes, sir.
Okay.
So similar arguments can be given for sine.
Yeah. Obviously, but like in that case, it will be 0.
Zero.
It will be 0.
Zero, sir.
Yeah.
Zero.
Okay. Okay. So any other comment? Okay, then let's move to next problem.
So this was a good problem, sir.
Okay, yeah. So now let's move to what is this? Okay, yeah, this is also interesting. Okay, so this was fifth problem maybe. Okay, so fifth problem, like let me give one particular case, or I should not say in that way. So, okay, let's see what the question is. Then you will get what I'm trying to say. So, suppose you have been given a sequence xn, be any sequence of real number such that, okay, limit of, okay, let me give this part first, minus xn is equal to 0. Then you have to check, then prove or disprove xn is convergent. Okay, so maybe this I can say as the first part. Okay, then I'll state the second part. The second part is that, suppose again the same thing, copy paste such that this xn plus 1 minus xn is less than equal to some constant times r raised to the power n. So for some constant c greater than 0 and r such that, so and r less than 1, okay, and it's greater than 0 as well. Okay, so now this is the problem. So the first part says that suppose that the distance or the gap between the two consecutive terms are going to 0. That means they are very close to each other, the consecutive terms. Okay, so can you say the sequence is actually convergent? We know that Cauchiness implies convergence, right? That means after a certain time, if the sequential terms are very close, then we know that the sequence is convergent, right? So what does Cauchy means? Cauchy means that xn minus xm is very small for nm greater than some n naught, right? So after some stage, the sequential terms are very close. Then you know that it's convergent. But this is not exactly the same condition. This says that you are just knowing that the consecutive terms are close. Okay, but intuitively it must, I mean, you must feel that this should imply Cauchiness, right? That if
Sir,
two,
this should not be so true.
this need not be true. That's
Yes.
fine. Yeah, but do you have an example?
Sir, take sequence as minus 1 to the power by n.
Okay, let me check. So, okay, so the example what you're saying is xn equals to
Minus 1 raised to the power 1, n.
n. Okay, will this example work? How will this example work?
Sir, that sequence converge, no sir, it will converge to 2 sir, modulus xn plus 1 minus. It will not work sir.
Exactly, so that the gap is always going to be 2. I mean,
Yes sir, yes.
huh? Okay. Okay, so at least some of you are feeling that this should be false. Anyway, but it's a bit counterintuitive in the sense that you know that two sequential terms are close. Okay, now, so suppose xn naught in roughly what I should say is xn naught is close to xn naught plus 1. Okay, this is close to xn naught plus 2. This is close to xn naught plus 3, and so on. But you cannot say this xn naught and xn naught plus 3 are close. And this is why it's making it false, that the sequence xn might not converge. So the condition that two sequential terms are close to each other does not mean that after some stage the terms will be close to each other. Are you getting what I'm trying to say?
Yes sir.
Yeah.
Yes sir.
Okay, so now, okay, so if I'm saying that this is false, I should give some example. So can you think of some example? So try to think of a sequence where they are close each other, like two consecutive terms are close, but ultimately they are not going to converge. Okay, so at least tell me what is the best example you know of a divergent sequence? I think from there one can guess the most simplest example that you know.
It is 1 by n.
No, I'm saying give me a sequence which diverges.
N.
Xn equals to n wall, right? So this is the most easy example that you know. Okay. Now I'm saying that if I define xn plus 1 minus xn, I'll getting 1. Okay. So the gap is always going to be 1. So okay, this is not going to serve for my example, like for this case, because I need that at limit this should go to 0.
So n minus 1.
No, whatever you do, if you add any constant,
Yes, sir,
it's not
minus 1. Okay.
it's
It
not
will
going to
cancel
help,
out. Yes.
right? But what you can do is, okay, now the other thing would be what if we take some square of this? So let's say yn is n square. Okay. Also we know this is divergent, but what will be the difference of yn plus 1 minus yn? This would be n plus 1 minus n square. This would be n square plus 2n plus 1 minus n square. So this is 2n minus 1 plus 1. Again this is going to infinity. Now see a difference between these two things. Here what you got is the difference is constant 1, but here the difference is going to infinity. So what, instead of taking square, so this will work. Okay, so this will work. So if I define Zn to be n or xn raised to the power alpha for any alpha greater than 1, so the same argument will work. You will see that Zn plus 1 minus Zn will go to infinity. That means what if I take alpha to be less than 1? So for example, what if I take my Zn to be n power half? So instead of taking square, I got to know that when I am taking square, the rate is increasing of the difference, right? Here I was getting 1, here I got n. So what if I take square root? Can you tell me what will be the behavior of Zn plus 1 minus Zn?
So it will converge to 0.
It will converge to 0, right?
Yes, sir.
So this will be this. Now, once you rationalize this, what you get is n plus 1 minus n upon root n plus 1 plus root n. Now you know this goes to, so this n will cancel, will get 1 and this goes to 0. Okay. So here you can see that the two consecutive terms, you can see that root n plus 1 and root n are very close for large n, right? For large n they are close. If you plot the graph, you can see what is the plot of root x. It would be like this kind of thing, right? This kind of graph. So you see ultimately it's asymptotic, like this kind of thing. So they are close, but if you compare this term with this term, there has a quite significant gap. They are not very close. So what it seems that this term is very close to the consecutive one, but if you look at this term and at a bigger place, then they are very differences. There is some significant difference. Okay, so if you zoom in, so what I'm saying is, so this looks like this, that asymptotically it goes like this, but when you zoom this picture, okay, you will find that this point and suppose some corresponding to this point, this height will have a difference. Okay, so that's what this example shows you.
Sir, can we claim this sequence is monotonic?
Monotonic means?
Increasing or decreasing?
Yeah, this sequence is monotonically increasing, right? Xn equals to root n.
Sir, from that, sir.
Okay, you are saying that this is increasing, so it won't be convergent.
No, sir.
What do you want to say?
I want to say that if the condition is satisfied, then the sequence is monotonic, sir.
Okay, if this condition is satisfied?
Yes, sir.
No, you cannot say. So suppose I give you this sequence. So let's say 1 by n and minus 1 by n, kind of like oscillating. So suppose if n is even and if n is odd, right? So like once you will get 1, the other time you will get minus half, other time you will get 1 by 3, like this way, right? Or opposite way. So maybe here I should write odd or even. Okay. So anyway, this is converging to 0, right? So this condition has to be satisfied. But you can clearly see that it's neither monotone increasing nor decreasing.
Yes, sir.
Yeah. Okay. Okay, so this is xn is root n. Now you can clearly check. So this xn plus 1 minus xn, which is equal to root n plus 1 minus root n, is nothing but 1 upon root n plus 1 plus root n, and we know this goes to 0, okay, as n goes to infinity. So that is limit of xn plus 1 minus xn is equal to 0, but xn diverges to infinity, okay, since it is unbounded. Okay, anyway, I'm not writing, it's obvious. Okay, so the first example shows you that closeness between two terms cannot guarantee you that the sequence will converge, right? In the second question, you see this condition is satisfied. But along with that, what you know is that you know how it goes to 0. It goes to 0 in this fashion. That means it is bounded above by something, okay? And that you know the rate, at what rate it is going to 0, okay? So because of that, in this case you can actually prove that this sequence xn is convergent. Okay, so how should you approach to prove this result? So I have already said the answer, that here you have to prove, okay? So how you should prove? Although I have already pointed out that what is the difference between this and Cauchy-Ness condition. So what do you feel, if you want to prove something is convergent, what should be the approach in this particular problem? Okay, so the approach would be, so what I said here is that, see, this condition is not telling me that the sequence is Cauchy, but over here I'm saying that this condition is making it convergent. So that means I should try to show that this condition will actually give me that the sequence xn is going to be a Cauchy sequence. Okay, and why should I approach in this way? Because I know in Cauchy sequence what do I need to do? I need to find a difference between this kind of term, and that I can do it in this way: xn minus 1 plus, like this, at last xn plus 1, xn plus 1 minus xn, and I know estimate on these terms. So using the estimates of these terms, can I conclude that this is also small? So that's the goal. Okay. Okay, so now let's try to do this. So what I need to do is, so suppose let n comma m belongs to the natural number, and let such that you are choosing n to be greater than m. Okay, so now I would like to find, okay, so here also I should write that let epsilon be greater than 0. Okay, so now I want to estimate this xn minus xm, right? For Cauchy, this is what I need to do. So this I can write it as xn minus xn minus 1, okay, because I have assumed that n is larger than m, okay, and then xn minus 1 minus xn minus 2 plus dot dot dot. Ultimately what you get is xm plus 1 minus x of m. Okay, now you already know the estimate of this. This is the plus point over here. In the earlier case you don't know the rate, so you know each of the term will go to 0, but you cannot conclude that this will also be kind of very small. You cannot conclude that, because it could happen that suppose everything is less than some constant 1, okay. So if I say 1 plus 1 plus 1, then what I am getting is this is equal to n minus m. So if I get any constant, I'm getting this kind of behavior. So basically what I mean to say is, using the fact that this difference is converging to 0 for large n, you cannot conclude that this difference is also going to converge to 0, okay. That's the main thing, because this n minus m can play a role and can contradict the things. You can check in this example, for example, okay. Okay, but over here we know the rate, precise rate at which it goes to 0. So now this is less than equal to some c times r raised to the power, so n minus 1, and this is r n minus 2 plus dot 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 plus r m, right? This is the bound what you get. Now from here what you can do is, you can take, this is the least power, you can take common outside, so c r raised to the power m, and then you have 1 plus r plus dot 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 plus r, so this term would be n minus m minus 1, okay. Now what do you know, this is a kind of, so this I can write, this is summation r raised to the power n, n from 0 to infinity kind of thing, okay. If you want to use this, you can use it, and you know this is less equal to 1 upon 1 minus r. This geometric series, you know that this geometric series converges to 1 upon 1 minus r. If r is less than 1, then you can do this, okay. So in case over here you already know r is positive, so r is less than 1. So now you know that this is something constant, this you can bound it by something constant. This is a constant number, right? It is not depending on n or m, but and also you know this is going to 0 for large m, so this converges to 0 for m belong, if n goes to infinity, right? So you can make this term very small as per your wish, right? So what I can say is that this whole term, I can say this is less than epsilon if m is greater than equal to m naught for some m naught belonging to n, okay. So this proves that the sequence xn is Cauchy and hence convergent. Okay, is this clear?
Yes, sir.
Okay. Okay, then let's, if it's fine to everyone, we can proceed to the next problem. Okay, so let me see. Okay, so now let me write this question. So this was 5th. Okay, so 6th, like again I have a few parts, so you can keep on thinking. I'll just state till then you can think. So the first part says that suppose, okay, so for let me write, let xn be a sequence of real numbers. Okay, first part says that suppose the subsequence x2n and x2n minus 1 converges, will xn also converge? Okay, so this is the first part. The second part is, suppose x2n and x2n minus 1 converges to same limit point. Will xn converge? Does xn? Okay. Third part is that suppose x2n, x3n and x2n minus 1. Let me write this first. Converges. Does xn converge? Okay, so first, what do you think? So first one is easy, quite easy, right? What do you feel?
Need not converge.
Right, so we cannot say. And what will be the counter example?
Sir, 1 minus 1, 1 minus 1 to the power n.
Correct. So we know that xn minus 1 raised to power n. So this does not converge. But x2n is equal to 1 and x2n minus 1 equals minus 1 are convergent. Okay. Now what you find in this example, you saw that both the sequences are converging to two different limit points, right? So the second question asks, what if the limit points are same?
Convergence.
It should converge. Okay, so do you know the proof, or I just want to know whether you know this or not. So have you seen these results earlier?
Sir, these two sequences forms the complementary pair of the subsequence.
What
Means, sir, if you collect the terms of these sequences, then it will form the original sequence. Terms of the original sequence.
Yeah, that's what subsequence means. Because
Sir,
x
complementary pair of subsequence, I am saying, sir. Sequence x2n and sequence x2n minus 1
correct.
forms complementary pair of sequence xn.
Okay, what you are saying is right, that is true. Okay, so you are saying that just because the union is equal to xn, so you are saying that they will converge.
And converging to the same limit points.
Correct. Yeah, you are right. So basically, so what he's saying, I'll just write it in few lines. So okay, so let this x2n and x2n minus 1 converge to x. Okay, so my claim would be that xn converges to x. And why it's so? Because you can see, as he is pointing out, the proof goes like this. So you want to estimate this xn minus x. Now what you know, that this is equal to x2n minus x, or I should not write 2n, x2k, or 2k minus 1 minus x, right? If n is equal to 2k and if n is equal to 2k minus 1. Okay, and you know that this x2k and 2k minus 1 both are converging to x. So what you know, you can say that this is less than epsilon if your k is greater than equal to some k naught, or k1. Okay, and from here what you know is this is also less than epsilon if k is greater than equal to some k2, right? So I am using these results. x2k and x2k minus 1 converges. So using that I know that this will happen. Okay, now what does this mean? This would simply mean, so basically in terms of picture what I can say is that suppose this is x1, x2, x3, x4, so on. So you know that this pair is going very close to some x, and you also know that these things are also going very close to this number. So obviously as a sequence, if you look collectively, it is going to close to this x. That is the obvious thing, right? Yeah. So I'm just writing in mathematical, but it's actually very easy. Like you just have to understand what it happens. So this is what he means by complementary, that both of the all the terms, you know information about the whole sequence, because the converging limit point is same. So you know this also goes to this also goes to 0, I mean some x, and obviously the whole sequence will go to that point, because the sequence is made up of these two subsequences only. Okay. Okay, so from here what you can say that n which is equal to 2k is greater than 2k1, and from here you can say n is greater than equal to 2k2 minus 1. So you just have to choose for n greater than maximum of these two, 2k1, 2k2 minus 1, your xn minus x is going to be less than epsilon. Okay, so that's how you can prove it. Okay, now the third part is a bit interesting. Okay, so what you know is that this is okay. So even sequences, subsequence, odd subsequence, both are converging to some point, same point, then you know that the sequence is converging. What about the third one? About third one, you know nothing about the limit point. What it says that suppose the odd sequences goes to some point, even sequences go to some point, and x3n, which is the multiples of 3, goes to some point. You don't know what the points are. Okay. Now the question is, will the sequence xn converge?
Yes, sir.
Yeah. So how will you prove that?
Sir, we have to prove, sir, limit of these sequences are equal, sir.
Okay, so like by the previous one we know, we just have to prove that the limit of this and this are same, then we are done.
Yes, sir.
Right? So do you have some idea like how to prove this?
Sir, if we, sir, make some sequence which is, sir, contained in x2n and some is and is also contained in x3n, sir.
Correct.
And
Yeah, I think your approach is right. What you are saying is like you have to work in that direction only. That is for sure. Okay, so let me write properly what it means. So suppose x1, so you have two sequences. Okay, so x2n, you can write it as x2, x4, x6, x8, and so on. Then you have another subsequence which is x2n minus 1, which is x1, x3, x5, x7, and so on. Okay. Now you have another subsequence x3n, okay, which is x3, x6, x9, x12, and so on. Right. So now
sir,
suppose.
if we take, sir, if we make a sequence x6n, sir, so then it will be, sir, contained in x2. It will be subsequence of sequence x2n and sequence x3n.
Correct.
So, sir, sequence of x2n and x3n will be, sir, same.
The limit.
And the limit, yes, sir,
Yeah.
limit. And then, sir, 3, 5, if we take multiple, sir, 3 into n square.
Okay. 3 into n square will not work, but okay, understood. What you are saying is actually correct, but you have to just write in the proper setting, that's all. So what you are saying is completely fine. So what you can see, so more precisely what it says that you are saying that this, you are getting one time odd, one time even, one time odd, one time even, right? This is how it works. The table of 3 is 3, 6, 3, 6, 9, 12, 15, 18. So once you are getting even, otherwise odd, again even, odd, like this, the process continues. And we know that something even is contained in here, odd is contained in here. And that's the information what you need to use. Okay. So suppose that this converges to x, suppose this converges to y, suppose this converges to z. Okay, now I'll choose two subsequences as you said. Okay, so the first subsequence would be this thing, so I'll just write in short maybe x 3 times 2n.
Sir, if you take, sir, 3 to the power n, sir, x 3 to the power n.
X 3 to the power n, 3. No, no, but again, there are something which will be missed out, right? X 15 will be missed out. Okay, so I'm just trying to make it complementary only. You can do
No,
with
sir.
that.
No, sir. Sir, we have, sir, x2n and x2n minus 1 as a complementary pair of sir sequences.
Correct.
And if we are able to show that sequence x2n is converging to x2n and x2n minus 1 converging to same limit, then the whole sequence will converge to this.
True.
So, sir, I will show that the sequence x2n is converging to L and x2n minus 1 is also converging to L, sir.
True.
Sir, for this, I, sir, gave you, sir, first sequence, sir, that x4n, sir. And for second, sir, take, sir, x3 to the power n, sir. Are you not getting, sir?
I understood. But again, you will have to write two lines. Okay, so let me tell you. What you are saying is absolutely correct, but then you will have to write two times. So what I am saying is this one. Suppose you write x4n. Anyway, x4n will not come. x6n, what you said, will come. Right? Because 6, 12, 18.
Yes,
that will come. But the point is, see, you have to say this is a subsequence of this and this is a subsequence of this as well.
Yes, sir.
And then you will say that x and z are equal.
Yes, sir. And both again, are convergent, so subsequence also converges.
Yeah, and the limit point would be same. And the other one?
Yes, sir. And the second sequence, if you take x3 to the power n, sir.
Okay.
Yes, sir. Then it
again,
will contain.
You will have to say that this is a. So anyway, like the problem is that what you are saying is correct, but how do you prove it properly? So what I'm saying is, so over here, then you will have to say, okay, the 3n is odd for all n. Okay, and then only you can say that this is subsequence of this.
Yes, sir.
The second thing what you need to say is,
it will not be, sir. It will also contain in, sir, x3 n, sir.
Yeah, so that's what you have to say. I know it's true, but then you'll have to say 3n is contained in 3n, right? This set. So how do you prove this? So suppose y equals to 3n. Okay, then it's fine. That 3 times n minus 2, n minus 1.
Multiple of
and
then
this is 3 times k. Yes. Okay. So this is how you'll have to write. That's all I'm saying. You can do it, but this is how again you'll have to prove that this 3n is going to be odd.
Yes, sir.
Right? You'll have to argue that how you are saying that 3n is odd. So you'll have to prove something. Okay, so
yes,
this
sir.
is a correct way. You are finding a subsequence which is, so main idea is that you have to find the subsequence of this, which is a subsequence of this also. Then you can say x is equal to z. Another is you have to find a subsequence from here, which is a subsequence of here as well, so that y and z are same. That's the idea what you are saying, and that is absolutely fine, no issue. Okay, but what I'll choose is much more simpler, like so that I don't have to do any work at all. Okay, so the simplest thing would be, one is what you said, 6n, that is 3 times 2n I'll do. Okay, and this is same as x times 2 times 3n. Okay, you can clearly see both are, I mean the way it has been written, it's clear that this is subsequence of this and this both. In the second one, what I'll do is x 3 times 2n minus 1. Okay, and now if you see 3 times 2n minus 1 is what? This is 6n minus 3. So I'll take 2 common, I'll get 3n minus 1. So sorry, 3n minus 1 minus 1. Yeah, so this is equal to x of 2 times 3n minus 1 minus 1, right? Now you can clearly see that this is subsequence, I mean the way it is written, subsequence of x2n and x3n. this tells you this is subsequence of x2n and x2n minus 1, sorry, x3n and x2n minus 1, right? The way it has been written. Okay, so this ultimately tells you, this part will tell you that x is equal to z, and this part will tell you that y is equal to z, and hence x equal to y equal to z, and then by b part you get that xn is convergent. Okay, so is this clear to everyone? So I hope this is fine to everyone, that how x is equal to z, because I am saying that this subsequence, we know that every subsequence will converge to the same limit. So now this is subsequence of this, so it will converge to z, but this is also subsequence of this, so it will converge to x. So hence x is equal to z. And this is how I am saying this. Okay. Okay. Okay, so now let's move to the next problem. Okay, so let's move to 7th problem. So what is next one? Okay, again. Okay, so now I'll discuss a problem which is based on monotone convergence theorem. Okay, mainly. So what it is, so I'll just write it. So I'm giving you already the hint, you better try to think when I'm writing. Okay, so
Sir, also discuss some problems from Cauchy sequencer.
today I haven't prepared much for Cauchy. That's what I think one problem I chose for Cauchy sequence, which is what I discussed already. So
Yes.
for today I don't have any problem. But what else? So you want to say that Cauchy is convergent, like this kind of problem, that if I'll prove this is a Cauchy, then it is convergent. So are you facing some difficulty in proving that something is Cauchy? Is it?
Yes, sir.
Okay, so do you know how to prove this xn? So how should I? So let me take this example only. So you know this is Cauchy. Do you know how to prove it?
Sir, in real, sir, Cauchy implies a convergent, and convergent implies Cauchy, sir.
Correct. That is true. But I'm saying that what's your, I mean, why do you want problem to be discussed on Cauchy? Because is it because you are facing difficulty in proving something is Cauchy?
Sir, in some examples, sir, we try to prove, sir, it is not Cauchy, sir. Then, as in this theorem, sir, use, sir, the Cauchiness. How to prove, sir, some sequence is not Cauchy?
No. If you want to prove something is not Cauchy, then I mean
If
you will have to use
also not know how to prove it is convergent, then.
Okay, so you are saying that in some problems, when you want to prove something is not convergent, it's easier to prove something is not Cauchy.
Yes, sir. Yes, sir. Yes.
Okay. So I don't know. I don't have any example in mind at this point.
Sir, in next session we can discuss.
So, okay, I mean you can pick. Okay, maybe I don't know what kind of problem you want to discuss. But anyway, if you have some problem like this, you can obviously mail me. Okay.
Okay, sir.
Okay, because at this point I can have easier example like xn minus 1 by n or xn equal to n, like this kind of problem I can discuss. But this is something that you already know. I think what you want is something a bit tricky problem.
सर कभी कभी सर सम में दी होती है ना टर्म्स, तो सर वहां पर फिर कॉसी सर ज्यादा यूजफुल हो जाता है.
I can get your point, but I don't have any particular example in mind at this point.
Yes, sir.
Okay. Anyway, okay. So let's see this one. So let xn be a bounded sequence such that this xn plus 1 minus xn satisfy this lower bound. Okay, so this is true for n belonging to n. Okay, so you have to show that xn is convergent. Okay, so I have already given you hint that you have to use it monotone convergence theorem. That means like if a sequence is monotone and it's bounded, so in this case you have to say that this sequence xn is monotonically increasing. Okay, then you have everything is done. So, but obviously you can see that you cannot conclude that this sequence xn is monotonically increasing. So you have to do some manipulation. Okay. So do you want to think about it?
Yes, sir.
Okay, so I'll wait for 2 minutes maybe. So did you get any idea? Okay, so see. So what you have been given is this thing, right? So let us look at this.
टू द पावर एन सर जीरो की तरफ कन्वर्ट करेंगे.
So what?
So sir, for large n sir, xn plus 1 minus xn will become greater than or equal to 0.
No. Greater than zero, okay, you're saying, but you know this is a negative term. So how can you say like it's going to zero, but from the left side, from here it is going to zero. So how can you say that it is greater than zero? It's not true, right? Okay. Anyway, like this sequence xn, you cannot prove. Like you cannot say it's increasing or decreasing using this directly. Okay. But what you can do is you can do a bit of manipulation, which is like this. So let me rewrite this one. Okay. Let me write it somewhere else in the solution directly. Okay. So what you have is xn plus 1 minus xn is greater than equal to minus 1 by 2 raised to the power n. Okay, which is same as writing xn plus 1 minus xn plus 1 by 2 raised to the power n is greater than equal to 0. Now my goal would be, can I write this term as, so I'll define a new sequence yn maybe, so that this becomes yn plus 1 minus yn. Okay, and now I can say that this is greater than equal to 0. Then this yn will be increasing, and using the boundedness of xn I can say yn is bounded. Okay, I'll define precisely what it is, and then using the convergence of yn I can say that xn will also converge. So what I can do is, so let me rewrite it again. This 1 by 2n, now my goal is what? I want to make it difference of similar kind of terms, right? So what my goal would be that I want to write, let me write it here. My goal would be that I will write this as 1 by 2n plus 1 and 1 by 2n. Can you think of writing it in this fashion? What do you think?
Sir, plus minus.
Yeah,
one,
that's what I'm asking. Like how can you write this term? Do you have any idea? At least what I can see, suppose I do minus, then what I can write, this I will make it 2 and 2n plus 1. So this is giving me minus 1 by 2n plus 1. Okay, so what I can do is I can write, so this suggests me that I can write this 1 by 2n plus 1 as minus of this plus of this, right?
Yes, sir.
So what I'll do is I'll write this xn plus 1 minus of xn. This 1 by 2n I can write it as 2 by 2n minus 1 by 2n, right? This is how I can write. Although I think I made it complicated, but this is the simplest way to write. Right? Just 2 minus 1, that's all. Now this is greater than or equal to 0. Now I'll club this one with this one, right? Because this is nothing but 1 by, okay, so let me write one more line. So this is nothing but 1 by 2n minus 1 minus 1 by 2n. So with higher this subscript, I will have to match the higher one, club higher one. So this I can rewrite it as xn plus 1 minus 1 by 2n, and this I can write it as minus xn minus 1 by 2n minus 1, right? So now I'll define my new sequence yn as xn minus 1 by 2n minus 1, right? Now you can clearly see, maybe star, from star we have yn plus 1 minus yn is greater than or equal to 0. This tells you that yn is increasing, okay. The second thing is that xn is given to you bounded, and this sequence 1 by 2n minus 1 you know converges to 0. So this is also bounded, so it is bounded as well, and this tells you that the sequence yn is also bounded, right? So we have obtained a sequence yn using xn which is increasing and bounded. So this tells you, so by monotone convergence theorem, yn is convergent, okay. And now if you look at this expression okay, star 1 then you can clearly see this goes to 0. So if yn converges to y, then xn will also converge to y. So from star 1 yn we can conclude that xn is convergent and limit of xn is same as limit of yn, okay. So this is how you can deal with such problems. So whenever you see that in sequence in question you have been given that this sequence is bounded, okay, like you should try at least this method, that if it's given that it's bounded, so there are two things. Once you know it is bounded, you know there is a subsequence which is going to converge, okay? That is Bolzano-Weierstrass theorem, that you already know, okay. But in here the question is that you want to prove that the sequence is convergent, okay. So whenever you want to prove the sequence is convergent, then obviously the one theorem what you know is monotone convergence theorem, and then your goal should be that can I prove that this is increasing or decreasing, something like that. From there it was obvious that you cannot conclude. Suppose it was given plus, then it was clear that this is greater than or equal to 0, and hence you can directly say that xn will converge. But here there was a minus sign, so you cannot conclude, right, that the xn is convergent. But using this you can construct a sequence yn which is monotone and which is bounded, and using that the limit of that convergence property of yn you can conclude that the sequence xn is convergent, okay.
So, sir, from here we cannot, sir, say that sequence xn is monotonic.
No, you cannot. Okay. How can you think? Is there anything what you are going to see? I mean, at least here it's no, saying sir, that the difference of 2 is greater than or equal to some negative value. So you cannot say that it's increasing.
Yes, sir.
Okay. Okay, now let's come to next problem. Okay, do you want some more problems from sequence, or should I go to some topological things which is related to nested interval theorem or something like that?
Yes, Satish.
Okay, so I have one good problem for sequence, but if time permits, I'll say, but okay, as of now, I'll just write the problem, okay? So this you can try by yourself. So suppose alpha, beta, gamma are positive such that alpha, beta plus gamma is less than equal to 1, okay? It's a bit easy, but at the same time, you'll have to, I mean, it looks complicated, but once you start doing it, you will be able to do it, okay? So now you define x1, we define a sequence x1 as alpha, okay, and define xn plus 1 recursively as xn upon beta xn plus gamma, okay, for all n belonging to, I mean all n greater than equal to 2, that's all, okay? So natural number, obviously. Then the question is, does the sequence xn converge? If so, what is the limit? Okay, so I'm leaving it to you, you better try it, okay? If you want, I can discuss, but so what do you think, should I discuss or should I go to some other property, nested interval maybe, whatever you say?
Sir, if time permits, then discuss it later, sir.
Okay, yeah, sure. Okay, so now let's go to some other problem. Okay, so related to some close thing. Okay, so I think in this week sir has started this topological thing for real numbers, okay, or
Yes.
Rn. So now onwards we'll go to topological things. So let's start with this closeness some problem. Okay, so let's start with the easier one. So suppose this is the set S, which is minus 1 raised power n upon n, where n belongs to set of natural number, okay? So your question is S closed? Okay, I think this should be easier for you. Yeah, tell me quickly so that I can proceed in for the next problem. No? Okay, closed means what? You know the definition, right? Not closed, okay? Someone has said not closed. Nice. So it is not closed set, that is for sure. But do you know what the definition of closed set?
Limit point belongs to that set S.
Exactly. So it's kind of like if you take the set of limit points, this is how we denote the set of limit point. This should be contained in the set S. Okay. In other words, so this is one definition. The other definition could be that the closure. Okay, so closure is nothing but S prime equal to S prime union S. Now once you know this is contained in S, this is obviously contained in S, and the other way is obvious because S is subset of this thing. So I mean, this is another way of saying this as statement only. Okay. The third could be using sequences. Okay. Using sequences, what you can say? If any sequence I take in S, so suppose if I take any sequence xn in S such that xn converges to S, x, then x has to belong to S. Okay. And this is how why this I mean this it's kind of all things are analogous, okay? All three things what I have said, if you assume any one of them, then that you can prove the other two, that's what I mean to say. Okay, okay, so I hope everyone is clear about the limit point and all things for the set. Do you know the definition of limit point? Yeah.
Sir, minus 1 and 1 does not belong to S, but they are limit points for S.
Correct. That is true. Okay, so that's exactly the answer. So okay, I think everyone is fine with the limit point. Then I will not go to the definition. So you can clearly see, if I take a subsequence xn x2n, which is minus 1 2n plus 1 by 2n, and this is nothing but 1 plus 1 by 2n, this goes to 1 x 2n minus 1. If I do, this is minus 1 upon plus 1 by 2n minus 1, this goes to minus 1. Okay, so this x2n, this belong to the set S. This x2n minus 1 also belong to set S, but this 1 and minus 1 does not belong to S. Okay, but 1 comma minus 1. So I have given you 2, but any one would work. So if you want, you can just forget about this. Let's just talk about that. So from here only you can actually conclude. Okay, so I should not set 2. So but 1 does not belong to the set S. Okay. Now the question is, how will you prove this? How can you say that 1 will not belong to set S? Okay, so let's look at the definition, how S is behaving. So for n equal to 1, you can clearly see this is going to be 0. S equal to n equal to 2, you know this is 1 plus 1 by 2
Minus
minus 2. Oh, this is this
correct, sir.
1 by 3 and so on. So if you see, the points of S are like this. So suppose this is 0, this is 1, this is minus 1, this is 2. So it says that when you are taking odd powers, okay, then it belongs to minus 1 plus something. So it is obviously always greater than minus 1, right? And it's going to be equal to 0 at some point. Obviously for n equal to 1, we know this is there. Okay, in case of odd even power, if you take, it is 1 plus something, right? So this is 1 plus something. Okay, and 2 will not be reached in this case. Okay, so I think this example is much more easier. Okay, so let me just point out this one only. This one is easier to conclude, at least. Okay, from here, so I can clearly say but 1 does not belong to S, since if I take any term x, which is minus 1 raised to power n plus 1 by n, this is always greater than minus 1, right? So set S does not contain minus 1. Okay, this is just easy from the definition, because this is a positive
Sir,
quantity.
always greater than minus 1.
Yeah, because this is a positive quantity, and the possibilities for minus 1
Minus
raised,
1.
yeah,
Sir, minus 1 plus 1 by n will be, sir, less than minus 1. Yes, sir. Greater than minus 1. Keep
yeah,
it.
because this is a positive thing, and
Yes,
this
sir.
is either going to be 1 or minus 1. So that is always strictly, I mean, okay, I should not say, but combiningly you can see that we are adding some strictly positive term to minus 1 and plus 1, then obviously it is going to be greater than minus 1. Okay.
Yes, sir.
Okay. Okay, so now let's go to this problem. Okay, so the next problem is, okay, let me come to this one, or should I? Okay, so I think this is mentioned in the assignment. So, okay, let me be a bit quick. So or let me go to the different problem. That's better one, because I have less time. So okay, so you have already learned this theorem called nested interval property of closed set. So I'll just mention the theorem once, and then I'll go to the question. So the theorem is like this. So suppose In be a nested sequence of closed intervals. Okay, so what does that mean? That means that is In equals to an bn, and this an. Okay, so when you go higher and higher, the value will decrease, or let me say this simply in this way, that an plus 1 bn plus 1 is contained in an bn. Okay, so this is what it means, nested and closed intervals. Okay, also, okay, so when you have this property that you have a sequence of closed intervals, okay, and there one more thing, bounded, I should mention, I missed it. Closed bounded intervals. Okay, so because an and bn are real number, that's all. So here an comma bn are in the real number set, so from there I can say it is a bounded. Okay, so now if I have a sequence of nested closed bounded interval, this would imply, the conclusion is that this tells me that intersection of in will be non-empty. Okay, n from 1 to infinity. The other thing is,
Sir,
yeah,
sir, when you are saying closed intervals, then it is, sir, clear that intervals are bounded, sir.
no, I mean this
Then why
is
you are, sir?
a comma infinity, this is also closed, right?
Yes, sir. Okay, sir.
Okay,
But, sir,
yeah,
bn belongs to R, sir.
yeah, that's what I've written, a and bn belongs to R.
But
I mean,
then you don't need, sir, to write bounded, sir.
no, I'm saying what is the meaning of the first line, so this is kind of in bracket, you can think.
Okay, sir.
Okay, so if you have this thing, then you know that this intersection is going to be non-empty. Additionally, moreover, if you say that the limit of length of in, okay, which is limit of, in other words, bn minus an, this limit is 0, that means the size of the interval converges to 0. In that case, what you have is, then this would imply that intersection of in is equal to some singleton set, okay, x. Okay, so this is what you have. Now my question to you are the following. So let me say this is some result. Now this is the question. The question goes like this. So suppose, what should I write? Where is the question? Okay, so maybe I should write directly. So suppose, okay, maybe I can say, how should I write it? Okay, maybe I'll just directly write. So what I want to mention here using the next three statements are the following. What I mean to say that these conditions, bounded, closed, are important. Okay, if you remove this condition, then this result won't be true. That's what I want to say. So the question can be stated in the following way, that consider or find a sequence of nested intervals, or closed also, nested closed intervals. Okay, bound. Okay, so first thing, let's check about the boundedness. In such that intersection of in is equal to phi. This is the first thing. The second thing what I want to say, find a sequence of nested open bounded intervals such that intersection of in is equal to phi. Okay, and the third could be like this. I don't know how should I write the third one. Let me see. Equals to, okay, let's just talk about these two. I just forgot what should be the third question. Anyway, okay, can you give me the examples of the first two? Okay, you just think I'll look for the third question probably. Just let me check. But you think about this one. Okay, let me see where it is. The moment you get the answer, let me know. Okay. Don't know where to find it out. Hmm. 83.
Sir, empty set is closed.
Yeah.
Sir, empty set is closed, na sir.
Yeah, empty set is closed, right? That are the trivial things.
Then we sir consider empty set with any sir nested closed intervals. Then
Okay,
it will
okay.
be sir empty.
Okay, that would be the obvious thing, but okay, I am non-empty, I should mention. Here also it's non-empty, okay? Hmm. Okay, so here also I should mention non-empty. Okay, anyway, that doesn't, because otherwise it's false. The statement what I've written is not true. So here also I'm looking for non-empty sets. The hint is already there, right? Because you have to look for some unbounded intervals. So go for unbounded intervals. Here also non-empty. Okay. Yeah, let me see. Yeah, this is the question what I got. Third one. So let in. And supremum of an and beta. Intersection of in. Okay. Yeah, so you didn't get, so you did not get the answer for the first and second part. So see, as I hinted out, like you just have to look for unbounded sequence, right? Unbounded intervals which are nested as well. Okay. So in you can think it as, so n comma infinity. Okay. These are closed and nested as well. Okay. But what will be the intersection of in? Are you convinced that this will be empty? Yeah. What do you feel? Yeah, that's obvious, right? Okay. So this is for the first part. Okay, if you want, I can just say. So suppose x belong to intersection of in. Okay, this would mean that x belong to in for all n, and this would mean x is greater than n for all n, which is not true, right? Because if you choose any real number, that has to lie between n and n plus 1. You cannot find a lower bound. I mean, for all n it cannot be true. You can say that there exists some n such that x lies between n and n plus 1, but you cannot say that x is greater than n for all n, right? That's not possible for a real number, okay? But this is a contradiction, okay? Okay, now for the second one, you have to find a sequence of nested open intervals, okay? But here I have added the thing bounded. So see, I am removing the condition one by one. So first I said just closed, okay, it can be unbounded. The second one is open, but it is open, not closed, okay? So do you have any answer for this?
So please show the question, sir, again.
Yeah. So I'm saying now just look for open interval which is bounded such that the intersection is again empty.
Sir, open minus n, comma n. No.
No, but then it's
Minus 1 by n, comma 1 by n.
you're saying minus 1 by n comma 1 by n, but 0 belong to the intersection. If you take intersection, you will get 0, right?
Sir, open 0, comma 0.
Exactly, open 0 and 1 by n if you take, you get so choose in to be 0 1 by n, this interval for all n belonging to natural number. And again this is open, bounded and nested sequence, okay? Or okay, but of open, bounded. Okay, but if you take intersection of in, this is going to be phi.
So that example will also work, sir. Minus 1 by n, comma 1 by n.
How? If I take intersection, I'll get 0, right? You see what you're saying is okay. I think you're right. Oh, because
So it's not close, sir.
It's not closed, right? You're right. You're correct. So this example is also going to work, right?
But this is simpler, sir.
In is minus 1 by n, 1 by n. Yeah. Again, this example is also going to work since. Okay. Fine. Now, let's come to the third problem. So the third problem says that you have a sequence of nested intervals, okay? So it's like this. So this is, let's say, a1, b1, then you got a2, b2, a3, b3 and so on, okay? Now you define alpha, which is an and bn, supremum of an. So it's like supremum of an will go to this side and infimum of bn is coming to this side. So it says that if you take the intersection, this is going to be alpha beta, and it obviously, if alpha is equal to beta, then obviously this is a singleton set, okay? So this is what you need to prove. So intuitively it's very clear, okay, that this should happen, right? Are you convinced that this will happen? Yeah. Okay, so now let's just write 2-3 lines to prove this. So what we need to prove that this intersection is going to be alpha beta, okay? So first we'll try to prove that intersection in is contained in alpha beta, okay? And the second one what I'll try to prove is the alpha beta is contained in intersection in. This is how we prove equality of two sets, okay? So now to do this, so let's prove this. So let x belong to the intersection in. This tells you that x belong to in for all n, okay? Let me write in next. X belong to in for all n, and this tells you that x lies between an and bn for all n, okay? Now if you take supremum over n for an, okay, so maybe from here you can write two inequalities, okay? Let us look at separately. So you know an is less than equal to x, you know x is less than equal to bn. Now from here, can you conclude alpha is less than x, and here x less than beta? So this is a question mark. Okay. So can you tell me how this is possible?
Sir, if all terms of a
Correct. All terms are.
sir, all terms of a set are less than some number, then maximum will be also less than that number.
It is not maximum, but supreme. Yeah, that is true. So how can you argue?
Supreme.
How can you prove this? I mean, this is something that you need to prove, right?
Sir, by sir contradictions.
Yeah, by contradiction. If you assume that alpha is greater than x, okay, suppose alpha is greater than x, then between x and alpha, since alpha is what? Alpha is supremum. Okay, so
Yes,
anything
sir,
less
there
than
will be
so
some numbers, sir.
exactly. So you just use the definition of supremum, okay, and that would contradict the fact that alpha is a supremum. So if you want, I can just say one line. So if x is greater than alpha, and you know alpha is the sorry, I wrote the other way around. Alpha greater than x, and you know that alpha is supremum. So and x is something. So this I am saying. How should I say? Suppose alpha is greater than x, then by definition of alpha, because x is something lying here, right? So that is the definition. If you subtract something from alpha, or if you have something less than alpha, then there exists some y in the set S such that x is less than y and less than alpha, right? And this would contradict the fact that alpha is.
This is the contract. Yes, sir.
So this is just a small argument. Okay. Anyway, now in the same way, what you can do over here is, so what does it prove? So this proves that alpha less than x less than beta, that is x belong to alpha comma beta. Okay. In this case, so you choose some y from the closed set alpha beta closed interval. Okay, and then you have to show that this belong to in for all n. So this will tell you, this is just very easy, alpha less than beta, and you know, like beta being the infimum, so where was the definition? Beta being the infimum is going to be an upper bound, right? So it's lower bound. So this is less than equal to bn for all n, and this is being supremum, it is an upper bound. So this is for all n, and this tells you that x belong to in for all n. This tells you that x belong to intersection. So this proves the other inclusion, right? So maybe I should. So this is how you can prove this, although this argument is quite easy. Don't have to do much thing. Okay, so that's how you can solve these problems. And what is okay, anyway, the second problem would use the same idea, so I'm not mentioning that. Okay, anyway, so that's all for today. Do you have any doubt?
Sir, you should write, sir, that problem, sir.
Which problem?
You are mentioning.
Actually, that will use this idea only. I think it's in the assignment sheet, that's why I don't want to mention that. So I mean, this is in the assignment problem, what has been uploaded.
Sir, can you show the slide where you have mentioned the inequality, the theorem, sir? Cauchy's second theorem.
Okay. This test you are saying, convergence. This one?
Yes. Okay, sir, fine.
Okay then, do you have any doubts or comments to make? If not, then we'll stop here. Okay then.